Now we're going to discuss examples of peephole optimizations and some subtleties associated with them. So we've seen this example. So let's say my original peephole optimization was if you move from R2 to R1, the first operand is the destination in these examples. And then you move from R1 to R2, then you don't need to do the second instruction at all because at this point we know that both R1 and R2 have the same contents. So you can just replace it with a single instruction, move R2 to R1. But can we generalize this to, let's say, both registers and memory locations? So for example, we want to say if you move R1, you can move the memory location, the contents of the memory location addressed by R2. So that's written parentheses $R2, which basically means in the C parlance, that would mean star R2, which means the contents at the location addressed by R2. Then you move that to R1, but you want to say that I want a single rule which tackles both register and memory locations. And so maybe you have a rule like this, where you have the slash to say this could be either a register or a memory operand. And similarly, this could either be a register or a memory operand, but then you have to be careful that when you are using a memory operand here, then you're also using a memory operand here, not the register. And then you can replace it with this. Well, it's possible to generalize these peephole optimizations in this way, and there are advantages and disadvantages of doing that. The advantages are, of course, that you increase the optimization opportunity. You can now capture more patterns through a single rule. However, generality comes at the cost of more complexity because it becomes harder to ascertain the correctness of a rule. As the rule becomes more and more complicated, it becomes harder to check whether it's correct or not manually. And people have done formal verification tools that will check whether peephole optimizations are correct or not to kind of alleviate this problem at least. But more importantly, it's harder for the compiler to pattern match while applying the rule. So when the compiler is basically looking at a program and using a peephole and dragging it across the program, it needs to make a decision on whether it has an opportunity to optimize a particular snippet of code or not. And if a peephole optimization becomes complicated, then the pattern matching becomes complicated as well. In this example, the pattern matching would need to check whether it's a register R2 or a memory location R2 and make sure that's the same thing that's being used in the second instruction and use the same thing at the replacement. More importantly, should it be matching a memory access that is addressed through a register only a register, or what if there was a displacement associated with it, and so on. So once we start generalizing it further, it becomes more complicated. This part of pattern matching becomes more complicated. A preferable alternative in many situations is just to use multiple peephole optimization so that the pattern matching remains easy. So for example, if I wanted to generalize registers to memory locations, maybe I just have three different rules: one for registers, one where the register is this. One where the memory location is the source operand, and one where the memory location is the destination operand in the first instruction. And notice that when I use the memory operand, I use this displacement mode. So 0 parentheses R2 basically represents R2 plus 0, and then access that location. So that's what this operand here represents. And so in this example, I have generalized. I have three different peephole optimization rules that tackle different patterns. In fact, having more peephole optimization rules is not that much of an issue because when the compiler is actually pattern matching, it can use some kind of order one lookup mechanism, for example, a hash table, to identify what's the right pattern to match with. And so the complexity of pattern matching does not necessarily increase by a lot if you have lots of peephole optimization rules, but it does increase significantly by the complexity of a single peephole optimization rule. All right. Also, there are ways to generalize that do not make it significantly harder to pattern match. So for example, in the previous example, we saw how a memory location had an offset or a displacement argument 0. But we can easily generalize it to any displacement argument I. So for example, just say that if it was a memory operand, then you can pattern match any immediate operand, any displacement operand, or any constant I, and I can also take the value 0, and in which case this becomes my generalized peephole optimization rule. The pattern matcher now only needs to check whether this is a constant or not, and then use replace, kind of create an association between I and that constant and make sure that the same constant is used in the second instruction as well. And so in the two rules that I showed in the previous slide with memory operands can be generalized using the displacement constant I instead of the displacement constant 0 that was shown on the previous slide. Notice that I may match any constant. Now, some Peephole optimization rules are more general than others. So there are other ways to generalize Peephole optimization rules. Let's take this example where we say that if you add 1 to A and kind of put it in A, and then you add 1 again to A and then put it in A again, then that's similar to saying that you add 2 to A and then put it in A. Well, a more general version is that instead of saying that it's the same register, maybe you want to say that the register that you add first from A to 1 is, you add A1 to A and put it in B. And the second rule probably says that you add B to 1 to B. There was an error in the slide. So now you add 1 to B and you put it in B. And now you can say that this, if you see this sequence of instructions, you can change it to add 2 to A and put it in B. I hope it's clear that this and this are equivalent if we assume that the only thing that the addition of instruction is doing is adding the second and third operands and putting the result in the first operand. Now notice, why do I say that this is more general than this? Because in this, B is allowed to match either a different register than A or the same register as A. If B is matched with the same register as what A matched with, let's say A matched with R1 and B also matched with R1, then this rule actually captures the semantics of the rule that we discussed on the top. But it also allows the possibility for B to match with a different register. And so this is a more general version than this version. Here's another way you could generalize the Peephole optimization rule. You can generalize the constants. So for example, instead of saying add AA3 and add AA4 and doing the constant folding by saying add AA7, you can say add AI for any arbitrary constant I, add AAJ for any arbitrary constant J, and then use this compile time addition operation called I plus J, which is computed by the compiler because I and J are constants, and then use that as the replacement. And so, this is more general because I can now pattern match with 3 and J can pattern match with 4, and I plus J would be equivalent to 7 in that case. But I and J can also pattern match with different other constants as well. Similarly, let's say you had a Peephole optimization rule which says if you multiply A by 4 and store it in A, then you can just shift A by 2 and shift it left. Well, instead of that, you can just say that, oh, the first argument here should pattern match with some power of 2. So one way to write that is 2 to the power I, in which case you can shift left by the log of that number, in which that one way to write that is that it should be shifted left by I. Now, notice that I am using these constants I, J, 2 to the power I in my patterns, which means my pattern matcher does increase. There's some complexity increase in my pattern matcher, because now when it looks at 2 to the power I, it needs to know that when it sees 2 to the power I in a pattern, in a Peephole optimization, then it needs to match it with a power of 2 in the actual constant that appears in the code. And so there is some increase, but these increases are usually practical enough and simple enough to be practically useful, and so these kind of things are done in production compilers. Now, I also want to point out here that, look, I mean, these rules that I showed you, for example, multiply A by 4 and store it in A, can be also generalized in another dimension, which is you can rename the registers to generalize them to take both the same register or different registers. But I haven't done that in this slide, but we could do that as well. And I'll leave that as an exercise for you. We've already seen that you can do constant or copy propagation and represent those kind of transformations or as Peephole optimizations. Here I'm doing constant folding. So if I move I to register A and then I move register A to register B, then I can just move I to register A and register B one after another. The advantage of this is that we are eliminating read after write dependencies on $A, so on the register A. So there's a read after write dependency, but there is no read after write dependency here. And if you remove such dependencies, it means that it enables more optimizations further downstream in my in my compilation pipeline. For example, it can allow these two instructions to now get reordered, whereas these instructions could not get reordered originally. Also, you can generalize through other mechanisms, and this is another common approach that is used by production compilers. So for example, let's say I had a Peephole optimization rule that said if you move a constant I to register A, and then you move a constant, move the register B to register A, which basically means that the value of A wasn't even used before it was overwritten, then you can just ignore the first instruction and just simply move the value of register B to register A, because the constant I in register A was never used. Well, you can generalize this in this way. You can say that if you ever move a constant I to register A, and at the end of this instruction, which is represented by a post condition, so I'm using the post keyword to say that. So it says at the end of this instruction, if the value stored in register A is not live, which means the value cannot be used in the future. In this example, the value cannot be used in the future because it's being immediately overwritten by another value, $B. So if the value cannot be used in the future, then you can replace this instruction by an empty sequence, which means you can eliminate this instruction. And so this is more general than this because it captures this, but it captures many other cases where the instruction after this may not have been move, but could have been add or something else, which basically ensures that A is not going to be live, or the value in A is not going to be used. To be able to kind of do such pattern matching, so let's say this is a Peephole optimization rule that my compiler has, then the compiler, when it's trying to pattern match a piece of code against this Peephole optimization, they need to check whether the register that has been pattern matched with $A, is it live or not at the end of this instruction. And for that, we need a prior analysis that identifies the live registers, or in other words, the registers whose value could potentially be used in the future at every program point. We're going to later study about data flow analysis, and we're going to study about liveness analysis on how to do this in an efficient and an effective way. But the point here is that a Peephole optimization can have such extra predicates. For example, here the predicate is a post condition that makes use of other analyses that have been done before the Peephole optimization was applied. In this example, we are using the liveness analysis. Here's another example. So just like we said that a register is not live, maybe a post condition says that the 0th bit of the register is not live. And so here's a Peephole optimization rule that is correct only if we are sure that the bit 0 of the register A is not live. And so the reason I put up this example is because I just want to say that in general you can make the post condition arbitrarily more complicated. In this example, I'm just going from liveness of whole registers to liveness of single bits within registers. And to support such post conditions, we firstly need a bit granular liveness analysis. So we need some analysis which says which bit of which register is live. This is possible, but it increases the running time of the compiler and also the complexity of the compiler. Moreover, you need to pattern match on this bit granular information. So the Peephole optimizer, which is going to use these Peephole optimizations to optimize your code, needs to pattern match on this bit granular information, which is a design decision that a programmer or compiler developer will need to make. Typically, such bit granular post conditions are not allowed in production compilers. Here's another example of a very impractical post condition. So for example, if I want to say $A plus $B is live, but the contents of $A and $B do not matter otherwise. For example, 1, 2, if A is 1 and B is 2, that is indistinguishable from A is 0 and B is 3. So while A and B are both live, it's only the value of A plus B that matters. And if that is, that's a post condition that I want, then that is much harder to both compute as a liveness analysis and to pattern match for the Peephole optimizer. And so, we've seen 3 different examples of post conditions. The first one was something that is relatively easy to implement and pattern match and is used by production compilers. And the third one, which is on this slide, is one that is completely impractical and does not make sense. And I don't know of any compiler that will ever, that will use these kind of post conditions. And the second one, which is a bit granular liveness analysis, is something that different compiler developers may decide to use or not use. Here's another example of a precondition. So let's say my architecture has an instruction which takes constants, but the constants are limited to, let's say, 16-bit constants. And let's say the machine was 32-bit, which means these registers are 32-bit. So, when I write an instruction like mul $a$b I, it means you multiply I by the contents of $b, and then you store that into register $a. And similarly, you can do that with J. And here is a Peephole optimization which says if you see these together, then you can replace this with I star j. This is similar to the constant folding optimization that we saw with the addition instruction. Just that here I have replaced it with the multiplication, with the twist that these constants can only be 16-bit on a 32-bit machine. So the registers are 32-bit, but the constants are 16-bit. Now notice that this transformation is not correct unless I have a precondition that I star j, the multiplication of the constants I into j, do not overflow. Because if they overflow the 16-bit value, then the value that I have here and the value that I will compute by the sequence of these two instructions will be different. And so these kind of conditions are also possible to write in Peephole optimizations available in production compilers, which means that the Peephole optimizer needs to pattern match the constants and also check whether these pattern matched constants meet the desired preconditions or not. So to summarize, Peephole optimizers are an important piece of the compiler infrastructure. They can appear at every level. For example, if I take the example of a TensorFlow or a PyTorch program, which involves a compilation of graph neural networks or neural networks in general to optimized code, then you can do Peephole optimizations on the graph of the ML operators, the machine learning operators, or on the MLIR or TVM representations of those programs, which involve matrix operations like matrix multiplication, matrix inverse, etc. So you can, for example, say, here's a Peephole optimization that says that if you multiply a matrix by its inverse, then you can replace it with the identity or something like that. These kind of things can also be represented as Peephole optimizations. You can write Peephole optimizations at the IR level. For example, LLVM, which is something similar to 3 or any other 3-address code IR. You can write Peephole optimizations at the machine IR level, which is after the IR, there is some IR that is just before the assembly code, where you can do your last ditch efforts to optimize code. And this is where most Peephole optimizers were originally written for, which is at the last very end of the compilation pipeline. You basically write these Peephole optimizations and a pattern matcher to tighten up the code before emitting it. Although over the years and over the decades, this idea of Peephole optimizations has been generalized not just to the last pass, but also to other transformation passes within the compiler. And finally, you can also write Peephole optimizers that directly work on the binary code or x86 assembly code, which is often written as a standalone Peephole optimizer. So you are given an executable that has been generated by a compiler, let's say, or maybe written manually, and then you have a Peephole optimization that parses that binary and does Peephole optimization and generates a new binary. So that's another way of doing Peephole optimizations.